Okay, we'll pick up with section 11.10 here. And I think we did this example last. We're finding a Maclaurin series for cosine of x, and so there it is. Okay, and the radius and the interval are going to be the same radius and interval as the one for sine x. Again, because the radius and the interval of convergence are the same for the differentiated series. So cosine of x is the derivative of sine x, right? So I can know before I even did this here that the radius is infinity and the interval is negative infinity to infinity, okay, which is the same thing as sine x. So, okay, let's try this one next. So what if we had f of x equals sine of x squared? Okay, well, one nice thing about building a Maclaurin series is that you can build infinitely many series then from that point. So all I'd have to do here is replace x with x squared. Okay, so I got x squared minus x squared to the third power would be x to the sixth divided by 3 factorial plus x squared to the fifth, that'd be x to the 10th divided by 5 factorial. And minus x squared to the 7th is x to the 14th divided by 7 factorial plus etc. Okay, and then using series notation, again, I'm just replacing x with x squared, so that's what I got there. And when I simplify this, okay, so 2 times 2n plus 1 would be 4n plus 2. Okay, and so here'd be the power series for sine of x squared. Okay, and here's another example. So what if I had the power series form for cosine of the square root of x? Okay, well, cosine of x is this guy right here, right? So all I'm going to do is replace x with the square root of x. Okay, and so if I go right to the power series form there, square root of x to the 2n. Well, the square root of x, that's the same as x to the 1/2. And 1/2 times 2n, that'd be n, so x to the n. Okay, so the answer would be the summation as n equals 0 to infinity of negative 1 to the n times x to the n divided by 2n factorial. Okay, here's another one. So what if I had cosine squared of x? Okay, now that's different from cosine of x squared, right? Because I'm squaring cosine of x, not squaring just x. So to do this one here, now I would not be able to just, you know, throw parentheses and put a power of 2 around this guy. Okay, that's not correct. Okay, so and it wouldn't be simplified also. The thing to do here is to use the power formula for cosine squared of x. Okay, so this is from chapter 7, right? So it's a 1/2 plus 1/2 cosine 2x. And the reason I did that is because now I get rid of the power of 2. And I know the Maclaurin series for cosine of x. So all I'm going to do is replace x with a 2x there. Okay, and when we simplify this, let's see. I'm going to have 2 to the 2n, and then I'm bringing in the 1/2 there. So 2 to the 2n divided by 2, that's the same as 2 to the 2n minus 1, times x to the 2n. Everything else is going to stay as is. Okay, and I've got, so my answer would be 1/2 plus the summation as n equals 0 to infinity of negative 1 to the n times 2 to the 2n minus 1 times x to the 2n divided by 2n factorial. Okay. Here's another one. So what if we had f of x equals 1 plus x to the k power? Okay. I want to find the Maclaurin series for that. So I've got to know the derivatives, and then also when I plug 0 into the derivatives, okay, because that's involved in the formula. Again, A is 0 here for when you have a Maclaurin series. Okay, f prime of x would be a chain rule, so bring down the power of k. K times 1 plus x to the k minus 1 times the derivative of 1 plus x, that's 1. And then f double prime would be k times k minus 1 times 1 plus x to the k minus 2 times the derivative of 1 plus x is 1. Okay, the third derivative would be k times k minus 1 times k minus 2 times 1 plus x to the k minus 3 power times the derivative of 1 plus x is 1, right? And that's etc. So that trend is going to continue there. Now, if I find the nth derivative, I'm going to start off with k times k minus 1 times k minus 2 times k minus 3, etc., right? Now, what's happening here is that it looks like the last number is going to be always one less than the derivative that you're on. Okay, so like here I got a k minus 2, I'm taking the third derivative. Here I got a k minus 1, I'm taking the second derivative. On the fourth derivative, I'm going to have a k minus 3, you know. And so it's going to be k minus n minus 1. But when I distribute the negative there in the n minus 1, I get negative n plus 1. Okay, so k minus n plus 1, that'd be the last coefficient. And then the power of 1 plus x, or I'm ending this with a 1 plus x to some power, right? But it's always going to be k minus something. And whatever number derivative you're on, that'd be the number that you're going to subtract from k. Okay, so here's the second derivative, I'm subtracting 2. Here's the third derivative, I'm subtracting 3. Fourth derivative is going to be k minus 4, right? So the nth derivative would be k minus n. Okay. Now let's go ahead and plug in 0 into these functions. So f of 0 is 1 to any power is always 1, right? F prime of 0 would be k times 1 to any power is 1. Okay. F double prime of 0 would be k times k minus 1 times 1 to any power is 1, right? F triple prime of 0 is k times k minus 1 times k minus 2 times 1, etc. So the nth derivative at 0 is just going to be all these coefficients that are in front of 1 plus x to the k minus n, because that term is going to go to 1, right? Okay, so now I'm finding a Maclaurin series, which is for 1 plus x to the k power. Okay, so 1 plus x to the k power, that is equal to, here's the Maclaurin series. Again, a is 0, so I got f of 0, which is 1, plus f prime of 0 times x minus 0. So f prime of 0 is k times x. And then plus f double prime of 0 divided by 2 factorial f double prime of 0 is k times k minus 1 divided by 2 factorial times x minus 0 squared. Okay, so that's going to be k times k minus 1 divided by 2 factorial times x squared plus, and then what's happening here is I'm just taking the, whatever that coefficient is, dividing by the number derivative factorial, whatever that is. So here would be a 3 factorial times x cubed, and it would be x to the n power, whatever number derivative you're on. So plus etc. So just in terms of a general formula here, I'm going to have all these coefficients divided by n factorial times x to the n power. Okay, and this is an infinite series, so I got to have the plus dot, 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 afterwards. Okay. Now, I'm going to let what's called k choose n. K choose n. That's going to be equal to k times k minus 1 times k minus 2 times k minus 3 times etc., all up to k minus n plus 1 divided by n factorial, okay? Which is basically all the coefficients that I've got in front of each of these terms here, okay? Now these are called binomial coefficients. So using this notation here, the formula that I have for my answer will be 1 plus x to the k power that is equal to the summation as n equals 0 to infinity of, okay, I'm going to have k choose n, right? Then times x to the n. Okay, so this series is called a binomial series. Okay, and that's terminology that you'll see in the book in this section. Okay, and as a note, this series is going to converge if the absolute value of x is less than 1. Why is that? Or where did I get that from? Well, this resembles a geometric series, right? K choose n is some number. So I got a number a times x to the n power. Okay, so well, I already know that a geometric series is going to converge as long as the absolute value of x is less than 1. Okay, and it's going to diverge if the absolute value of x is greater than or equal to 1. Okay, so it's resembles a geometric series there. Okay, so let's take a look at this example. What if I had wanted to find a power series for f of x equals the cubed root of 1 plus x? Okay, well, that's 1 plus x to the 1/3 power, right? So I can look at this as a binomial series. And that is equal to the summation as n equals 0 to infinity of k is 1/3, choose n, times x to the n. Now, in the expanded form here, here's what I get. Okay, so all I'm going to do is replace k with 1/3 in this formula here. So I got 1 plus 1/3 times x plus 1/3 times 1/3 minus 1, that's negative 2/3, times x squared divided by 2 factorial, plus 1/3 times negative 2/3 times 1/3 minus 2, that'd be negative 5/3, divided by 3 factorial times x cubed, plus etc. Okay? And then if I simplify what I've got here, I've got 1 plus 1/3 x, and then minus, it's going to be minus 2x squared divided by 2 factorial times 3 times 3 is 3 squared. That'd be 9. Okay? Plus negative times negative is positive, right? So plus 2 times 5 times x cubed divided by 3 factorial times 3 times 3 times 3, that'd be 3 cubed. Okay. The next term is going to be a negative, right? Because I'll have a positive times a negative times a negative times a negative. That'd be a negative. Okay. So it's going to be 2 times 5 times 8. What's going to happen here is that in the numerator, I'm just going to move in increments of 3. Okay. Times x to the 4th divided by 4 factorial, and then I have 4 3's that I'm multiplying there, so it'll be times 3 to the 4th, okay, plus etc. Okay, so this would be my answer then. Okay, now it says observe table 1 on page 804. Okay, so just to point this out, here's page 804 in the book. Okay, and on page 804 we have a table of Maclaurin series, and these are important Maclaurin series in the radius in the radii of convergence. Okay, so these are all series that we've done. Okay, and And here's, now the reason why they're giving you this in the book is because they're saying that there's going to be several problems where you're going to use these formulas over and over and over again. Okay, so there's no reason to, come up with the formula that we see here. We've already got this formula. Okay, and so we're just going to use it, for that particular problem. So I've got a geometric series. And then the one for e to the x, the one for sine x, the one for cosine of x, the one for tangent inverse of x. We saw that in the last section. The one for the ln of 1 plus x. We saw that in the last section. Right, and then here's a binomial series. Okay. And then the radius of convergence is there on the side there. Okay. Let's go ahead and stop the video right here at this spot. And now we've been looking at Maclaurin series, so I'll show you a Taylor series here in the next example. Okay, we'll go ahead and stop the video right here.